In this video, we are going to look at a graphical representation of inverses. So we already started talking about inverses in class, and we talked about how how a function takes a value from the domain and it maps it into a value in the range, and an inverse undoes whatever the original function had done. So for example, if a function takes an x value of 2 and maps it onto a y value of 1, its inverse will take that y value of 1 and go back to the original x value of 2. It undoes what it has done. So let's look at what that looks like graphically. So I have here a function graphed for us, this red one. This is the one we're going to take the inverse of. And I have the line y equals x. So it turns out a function and its inverse are reflections across the line y equals x. Well, that makes sense because if the domain are all the x values for the original function and the range of the original function are all the y values, and then the inverse reflects that, it undoes that. So it's going to flip-flop all the x's and y's. It's going to reflect them across this line. Okay, so let's analyze this function we have here. Think about your parent graphs that we just got done doing in the last unit, and you will realize that this is an x to the third graph. So what's the inverse of x cubed? So let me put that on here. This one is x cubed. That's its parent graph. And so I know the inverse of this one, the inverse of cubing something, is cube root. So the inverse is going to be the cube root, which you remember looks like this. So whatever shape I finish with, it should be something that looks like this because cube and cube root are inverses of each other. Now, obviously, this red one has been moved from its quote-unquote home position where this inflection point where it twists. That's normally down here at 0, 0, and this one is up here. So I know this graph is going to be moved from its normal position, just like this red one was, but I should have this basic shape just move somewhere else. So it would be helpful if I had some particular points that I could move. I had something to aim for. So I'm going to find some points that are potentially easy for me to move. So for example, this one on the y-axis. This point is exact, and so I'm going to be able to move it. This point, the x-intercept, well, this one's not exact. I'm going to estimate, but that's not a hard one for me to move. Now this one right here, where the function crosses the line y equals x, that point is not going to move. So think about when you touch a mirror with your finger, the reflection of your finger and your actual finger touch each other on the mirror, right? And the rest of you comes out into the mirror, so to speak. So that's what's going to happen with this. Any point that's on our reflection line is going to touch. It's going to stay on the reflection line. And then this point right here, our inflection point, so that's moved over 2 and up 4. And so our cube root graph is going to have a reflection of this particular point. All right, so what I did was I labeled those points for us so that we could reflect them a little bit more easily. You can see my y-intercept, my x-intercept, and my inflection point. So the point 0, 4. Well, if they undo one another, if they take what's been done to the function and undo it, the original function took the x value of 0 and mapped it onto the y value of -4. So my inverse function is going to take -4 and it's going to map it onto 0. So I'm going to have the point -4, 0. I'm just going to switch the x and the y coordinates. All right, same thing with this one. Now, for purposes of your graphing, I would not expect you to get 0.413. You're just going to estimate. This is a little bit less than 1/2, right? Because 1 would be right here. So 1/2 would be right here, and this is a little bit less than 1/2. And then here's our point up here, 2, 4, which is our inflection point, which means we moved our parent graph 2 places to the right and 4 places up. Okay, let's reflect those 3 points. So the point that we had right here, 0, -4, it's now over here, -4, 0. The point that was right here, 0.413, comma 0, well, that's right here, 0, comma 0.413. And this one, 2, 4, has moved down here to 4, 2. So what we're going to do is we're going to connect these points, and we're going to keep in mind that our end result should look like a cube root of x graph. So I'm going to follow the pattern that I have here just in a reflected manner. So this part right here is going to reflect over here, and this part is going to reflect up here, right? Because it doesn't move on this particular point. So this part reflects over here, and this part reflects up here. Okay, so let's see if we can do that. So from this point, I'm going to reflect, and I'm going to, oops, I went too far. Let's try that again. I'm going to reflect down like this. There we go. Okay, and now I'm going to go up, and I'm going to go through this point like that. Those should be connected. Sorry, you guys. I have a really hard time aiming with my finger on this screen. So that is what we are going to have. There is my connected parent graph. Let me draw that all connected together. So that's what it would look like all connected together. Okay, so I asked Desmos to graph that for us. Here's our original function, and you can see that cubed graph is right here. I moved 2 places to the right and 4 places up. All right, let's look at where that inflection point is on this graph. You can see that this time I moved 4 places to the right and 2 places up, which is what you see right here in the equation. 4 places to the right and 2 places up, because you remember the horizontal translation is on the inside and the vertical translation is on the outside. So here is an x to the third graph that has been translated, and here is an a cube root of x graph that has been translated, and they are reflections of one another across this line y equals x, so therefore they are inverses of one another. Okay, so let's look at kind of what that means. Remember we said that inverses undo one another. So if I were to take this f of negative x and I were to replace x right here, I'm just going to take that whole thing and I'm going to put it in there, then what should happen? It should undo itself. I should end up with what I started with. Well, what I started with was just plain old x, right? I took x and then I shifted it 4 places to the right and 2 places up. But if I want to figure out where it was to begin with, I should have just plain old x. All right, so let's look at what that looks like algebraically. So you can see that what I've done here is I have put cube root of x minus 4 plus 2. I've put it right here in place of that x, right? The minus 2, the to the third power, and the plus 4, those are all still right there. The only thing I changed is that I put x right here. All right, so I have the function and its inverse kind of put together to see what happens. So let's do some order of operations here. Let's simplify this. I'll go inside the parentheses first. And inside the parentheses, I see adding and subtracting. Well, adding and subtracting are inverse operations. They undo one another. Plus 2 minus 2, that's going to be 0. So what I'm going to be left with is the cube root of x minus 4 to the third plus 4. Okay, so I took care of what's inside the parentheses. I can't do anything else inside the parentheses to simplify. So now I'll do my exponent. Well, I've got a cube and I've got a cube root. Cube and cube root are inverses of one another, so they are going to undo one another. And what I'm going to have left is x minus 4 plus 4. And again, I have minus 4 and plus 4. Those are inverse operations. They undo one another. And so what I'm going to have left is x. So what happens is when I have a function and its inverse put together, this is called composition of functions. When I put them together, they undo one another. And what I have left is the original thing I started with, which is x. And I could also have done it the opposite way. I could have chosen to put the f inverse on the outside and the f on the inside, and I still would have come up with x because they undo one another regardless of which way you do the algebra. It's going to work out the same. All right, let's look at another graph. So look at the one I have here. This red graph is the one we're going to focus on finding the inverse of. Okay, so think through your parent graphs like we did in the last unit. What does this kind of look like? Hopefully it looks like exponential growth, right? So I've got a to the x, and I know that my a is bigger than 1 because it's growth. And here's my asymptote down here at -3, right? Remember, our technology can't actually show you the asymptote very well. My asymptote is here at -3, which means I moved my whole graph down 3. So normally my anchor point is right here. I would go down 1, 2, 3, but there's no anchor point here, which means in addition to going down 3, I must also have gone to the left 1, right? So that's what I have here. I have an exponential graph, which has been moved to the left 1 and also down 3. So that's going to look like this. If you were to write out the parent graph, you've gone left 1 and also down 3. Okay, we're going to do the same thing we did on the other one. We're going to find some points that we can reflect. So I know this one that is on the line y equals x is going to stay on the line y equals x because that's my reflection line. And then the same thing for this point here. This point where they intersect, that point is on both of them, and so it's not going to move. I'm going to reflect across that line. All right, and I know I have an asymptote right here. I can use that as part of my reflection. And I also know my anchor point has been moved to right here because it went down 3 and left 1. All right, so let's put some labels on there. All right, I've got my anchor point here at -1, -2 because it went left 1 and down 3. And I've got my asymptote right here at x equals -3, right? Normally it's at y equals 0, but it moved down to y equals -3 because I'm shifted the whole graph down 3. Okay, so let's see how we can use those. Well, this horizontal asymptote that's right here at y equals -3, if I do the inverse, remember my x and y swap places, so that's going to become a vertical asymptote at x equals -3, which is going to be right here. And my anchor point, which was right here, that's the point -1, -2. Well, I'm going to flip-flop the x and y coordinates, so it's going to be -2, -1. That's going to be right here. Okay, so now let's connect the dots. Well, right here, remember they cross. So they're going to cross right here, and then it's going to go very close to that asymptote without going over. Then coming up this way, I'm going to go through that point, and they're going to cross again over here. And I notice I have another point I can aim for. I've got the point 1, 6 right here. So when I graph on this side, that point 1, 6, what do you think it's going to become? It's going to become the point 6, 1, which is over here. So when I cross through here, I'm going to be aiming for that point 6, 1. All right, so there, the black one is my inverse function. It goes through that point, through the points of intersection next to this asymptote, and up here through this point 6, 1. And we have not yet learned what this type of function is called, so I can't show you the algebra of how they undo one another. This is actually going to be a logarithmic graph, which we have not covered, but exponentials like this one and logarithms like this one are inverses of one another, and they would also undo one another. If I did the function composed with its inverse, I would get x. And if I did the inverse composed with the original function, I would also get x. It doesn't matter which order you do it. You should end up with x both times because a function and its inverse undo one another and end up with where you started, which is just that plain old x.